In section 7.4, we learn about arc length or curve length. This actually looks a little bit like the distance formula or Pythagorean theorem. It's like an a squared plus b squared equals c squared, and you took the square root. Number one, it actually is a perfect square. It is 1 squared, so it looks a little bit like the distance formula from middle school, but then because it's not a straight line, it's a curve, we have to integrate. So it's a neat formula, and I'll show you how we use it. Again, this formula needs to be memorized. I think you're going to find that it's pretty easy to memorize it, though. Find the length of the curve y equals x squared from x equals 0 to 3. That's a piece of a parabola. As we know, the parabola y equals x squared, looks like this. The vertex is 0, 0, and then it comes like this. This is going to be the point 3, 9. Obviously, the origin being 0, 0. And I want to find the curve length between 0, 0 and 3, 9. So I don't really need that extra part of the parabola. I got a little carried away. Let me erase that. Actually, before I do this, what if that was a straight line? What if I just went right from 0, 0 to 3, 9? I'm kind of curious. Well, if I wanted the length of that green dotted line, I could just set up a little triangle and use Pythagorean theorem. Even middle school kids would know how to do this. Obviously, this side is 3 and this side is 9, just because it goes through the point 3, 9 up here. And I could just go 3 squared plus 9 squared equals c squared. So c will be the square root of 90. And the square root of 90 comes out to be 9.487. If you look at the curve, though, the curve is longer than the green dotted line. It'd be like a telephone wire kind of hanging down, having some slack. So I would expect that the answer won't be 9.487. It'd probably be maybe closer to 10, maybe in the upper 9s, low 10s. I've exaggerated the pictures slightly just to make the curve look like it's slacking a little bit more than it probably really is. All right, let's use our formula and find the exact length of the curve, not an estimate. We'll call the curve length L, and the formula calls for an integral, and it's from 0 to 3. We have to tell you when we want you to start and end, otherwise it's a bad problem. So those will just be given to you. And then it's a large square root. There's always a 1 plus. And then what you have to do is you have to take the derivative and square it. And then that goes in. And there's a dx at the end. There's a dx at the end because the 0 and the 3 are x limits of integration. So, all right, take the derivative, y prime. That'd be 2x. And then you square the 2x and put it in here. So 2x times 2x would be 4x squared. All right, now, I don't know if this is good news or bad news, but this is not integratable by hand. To be quite honest with you guys, most things in real life aren't integratable by hand. I've been really working hard, and your textbook's been working really hard to find all the ones that are. But most of them are like this. You can't use sub it, so you just put it right into your calculator and let the calculator do the work. And L will come out to be right around 9.747. I feel great about that answer because it is a little bit larger than the 9.487 that we found for C when we pulled it tight. It's got a little bit of slack in it, so it is a little closer to 10. So 9.747 units is the length of that curve. All right, let's do one more example. Like I said, this section is short and easy. There's no reason to overteach this. Find the length of the curve 9x squared equals 4y cubed. Blah. From 0, 0, you can tell it goes through 0, 0. It also goes through the point 2 rad 3, 3. And the curve has this shape to it. It's a concave down affair. All right, find that curve length. Well, all right, I'll start by getting y by itself. If I divide both sides by 4, I'll have y cubed. You may not want to write this down, by the way. I'm going to change my mind. Just want to show it to you. Equals 9/4 x squared. If you cube root both sides, you're going to get y equals, see, 9 and 4 are beautiful perfect squares, but they're not perfect cubes. So the 9/4 x squared is going to be tucked inside a cube root, or it's going to be to the 1/3 power. Ugh. And you have to take its derivative and then square that derivative. This is not going to be good. I'm going to bail out. Sometimes that'll happen to you. You'll be starting a problem and you'll see that, solving for y might be cumbersome a bit, and maybe solving for x is smoother. So let's try this problem again with an open mind. I'm going to solve for x instead. I'll divide both sides by 9. You can copy this down. I'm not going to bail out on this. So we have x squared equals 4/9 y cubed. This is going to be a lot better. Square root both sides. We don't need the plus minus because we're in quadrant 1. But square root both sides. And 4 and 9 are both perfect squares. So you're going to have 2/3. And if you square root y to the third, it just becomes y to the 3/2, which is no big deal. In fact, it's awesome. Because when you take the derivative, the power and the coefficient multiply up to 1. So you get 1 y to the 1/2. And when you take the derivative and you square it to put it in the formula, it just becomes a y. So this is breaking down beautifully. All right, let's come over to the right and we'll get our equation ready. As always, curve length is the integral. Now that we're using the y coordinates instead of the x coordinates, we actually don't have to worry about the 2 rad 3 either. We sort of jumped around that as well. We're just going to integrate from 0 to 3. It's going to be dy. Remember, it still has the radical and still has the 1 plus, but this time a y is going in. In fact, I don't even need a calculator for this, and in fact, I don't even need a u sub for this. This is how nice this is becoming. I rewrote it as y plus 1 to the 1/2 power. Up by a power, divide by the new power, and put the 3 and the 0 in. Here we go. I kick the 2/3 out as I usually do, so 2/3 in front. Okay, in goes the 3. That's going to be 4 to the 3/2. Again, from Algebra 2, 4 to the 3/2 will give us 8. Now let's plug the 0 in. That's going to be 1 to the 3/2, which is 1. So the bracket becomes a 7. 7 times 2/3 is the proper curve length of 14/3. So this curve right here is 4 2/3 units long. Well, we've tackled both examples that I made. Really, this is more or less a calculator section. It's one simple formula to know, and it's really pretty easy. The only other thing I have is once in a while you get an issue like this. What if there's no derivative somewhere? Remember, the formula calls for you taking a derivative and then squaring the derivative and integrating. But what if you have a corner or cusp or vertical tangent or something along the way? How do you find the length of that curve? Maybe it's a bouncing ball. It bounces off a table and then falls to the floor. I mean, it does have a length. And the answer is just chop it into 2 different problems. Chop it right at the cusp. Find the length of the green curve, because the green curve now doesn't have a cusp. Then find the length of the blue curve, which again does not have a cusp, and add the 2 lengths together. So again, you can get creative, and it's no big deal. And now we are done with Chapter 7.